This video continues our discussion on AI transformer. Here we discuss the decoder of an AI transformer in C++. Billy will begin by explaining the key components that make up a transformer decoder.
In the previous video, we discussed the encoder and various components of an AI transformer and their implementations in C++. As a continuation, here we discuss the transformer decoder. This figure is from the original transformer paper. The left block is the encoder and the right block is the decoder. As you might have noticed, the diagram labeled the inputs to the decoder as outputs. Here is the explanation of what is actually happening and why they labeled it that way. There are two modes of operation, training versus inference. The confusion arises because the transformer operates differently depending on whether you are training it or using it to translate. In the inference mode, labeling it outputs makes sense. When we use a trained model, say to translate a new sentence in English to Spanish, we feed the English sentence into the encoder, inputs. The decoder starts with just a start token. The model predicts the first Spanish word, la. Now, to predict the second word, we feed the first output word, la, back into the decoder. So, in inference mode, what goes into the decoder is literally the sequence of words the model has output so far. Therefore, from a deployment perspective, the input to the decoder is the previously generated outputs. The diagram in the paper is drawn from this inference perspective. However, when we are training the model, those outputs are not the model's own predictions yet. We are feeding it the ground truth, the correct Spanish translation, to teach it. So we would call the sample data inputs to the decoder. Now let's examine the components of the decoder. We call the input embeddings with positional encodings X. X is projected by the weights to produce the Q, K, V matrices, which are inputs the masked multi-head attention module. Technically, the mask is usually an upper triangular matrix that is applied to the attention scores before the softmax step. It sets the scores for future positions to negative infinity, so their attention weights effectively become zero after the activation function like softmax. In our discussion, we use the following parameters. We consider only one input sequence or the batch size is equal to 1. Target sequence length for the decoder is NT. Source sequence length for the encoder is NS. Model dimension is D model. Number of heads is NH. Head dimension equals DK equals D model over NH. Feed forward hidden size equals DFF. The decoder input X is an NT by D model matrix. The encoder output E, which is a cross input to the decoder, is an NS by D model matrix. Let's discuss the components of the decoder from the bottom to the top. The masked multi-head attention is computed in this way. The input embeddings X are projected to the matrices Q, K, and V by the weight matrices WQ, WK, and WV respectively. The dimensions of the weight matrices are D model times D model and Q, K, and V are NT times D model. The second step is to split Q, K and V into NH heads, each of which has dimensions NT times DK. The attention AQH, KH, VH of each head is equal to softmax of the masked product of QH times KH transpose over square root DK times VH. We then concatenate all the heads. Note that the dimension of the matrix product is NT times NT, meaning that every token attends to every previous token. We can let MHAX be equal to the projection of the concatenated attention or concat, QKV, times the output matrix W. This output will be passed to the add and norm module to produce X1, which is of dimensions NT times D model. X1 becomes part of the input to the next multi-head attention block, which is not masked. It is called cross multi-head attention because in addition to the decoder input, it also takes input from the encoder output E. In cross attention, The query Q is obtained by multiplying x1 to WQ. It has dimensions nt times d model, where nt is the number of decoder tokens. The key K is obtained by multiplying the encoder output E by WK. Its dimensions ns times d model, where ns is the number of encoder, or source, tokens. The value V is obtained by multiplying E by WV. Its dimensions are ns times d model. When we compute Q times KT, the resulting matrix has dimensions, nt by ns. This means that each decoder token attends to all encoder tokens, allowing the decoder to focus on the most relevant parts of the source sequence during generation. The output of the cross multi-head attention is passed to the add and norm module. There, it is added to the input x1 through a residual connection, and the result is then normalized to produce the output x2. X2 is then passed to the feed-forward network, FFN, where the computation is FFN x2 equals fx2 times w1 times w2, where f is an activation function such as ReLU. For simplicity, no bias terms are included. Each token is processed independently and identically, the operation of a position-wise feed-forward network. The dimensions are x2, nt times d model, w1, d model times dff, w2, dff times d model, ffn, x2, nt times d model. Thus, the feed-forward network first expands the dimensionality from d model to dff, applies the nonlinearity, and then projects it back to d model. Finally, the output of the feed-forward network is passed, together with x2, to another add and norm module. In this step, the feed-forward output is added to x2 through a residual connection and then normalized to produce the final output y. The dimensions of y are nt times d model. This output y becomes the input to the next decoder layer, that is, y becomes the new x. Only the output of the final decoder layer is passed to the linear module, followed by the softmax module, to generate the output probabilities. The output probabilities produced at the final layer are used to compute a single global loss. This loss is then used to update all the weights in the model through backpropagation. In general, all weights in each layer are independent of those in other layers. That is, the weights in layer 1 are not the same as the weights in layer 2. Encoder weights are independent of decoder weights. For example, the feed-forward network, FFN, weights in the encoder are not shared with those in the decoder. Each FFN has its own weight matrices W1 and W2. No weights are reused across layers. All parameters are learned independently. Although there is only one global loss, computed after the softmax layer, this loss is backpropagated through the entire network, updating all weights in every encoder and decoder. We will omit the weight update procedures from this discussion. These will be covered in detail in a forthcoming video.
Thank you, Billy. The following is a C++ implementation of the decoder. We discussed most of these functions before. The util.h is the header file of the helper functions. These are the actual functions, okay, util.cpp. Okay. So we type def matrix D to be a two-dimensional vector of double. F is an activation function. This softmax is a 1D softmax activation function with 1D input vector. And this, we override the name. It has a 2D input vector. And add mat is to add two matrices. Okay. And it returns the sum. Transpose calculates the transpose of a matrix. mat will multiplies two matrices A and B and returns the product. Init matrix is to initialize a matrix M with dimensions n times m. It does that. We have a random number generator with standard deviation 0.2 here. Print dictionary is to print an unordered map. Print matrix is to print a matrix. Add and norm is to add two matrices A and B and then does the normalization, okay, and returns the result. Scale a matrix, scale mat, basically is to multiply each element of the matrix A by a vector S. So this is a new function that we did not have before. And also the scaled attention. Before we used it, we do that in a class, but we put this in the helper function. So it calculates the scaled attention with inputs, matrices Q, the query, K, the key, and V, the value matrix. Okay, and also there's another parameter called mask, which could be false or true. If it is true, then we add a mask to the matrix, to the output. So it is pretty straightforward. We first find the transpose of K, and then get Q times K transpose, and then that's the scale. And if it is masking, that means if mask is true, then we set the upper triangular part to be a large negative value, so that after the activation function, those values will become 0. Okay. And at the end, we do a projection, okay, of, well, not a projection, basically it is A multiplied by V. Okay. So it is this part. Okay, so we first we do this matrix multiplication, scale it, okay, and then times this, okay, and then, well, after softmax we times this. Okay, that's what their function does. Okay, the scaled attention. Okay, and then we return the output. Now this is the transformer classes we discussed before. So this is the header file. Okay, the actual implementation. Okay. The tokenizer class. Okay. And the embedding class, we discussed all this in a previous video. And positional encoding class, and this is the multi-head attention class. Okay. So it has the weights WQ, WK, WV, WO. It starts with some random values. Okay. And this function compute attention will compute attention with or without a mask. So it has inputs XQ, XK, XV corresponding to QV key and value. Okay. And we do a projection. Basically, it is a matrix multiplication of the X input with the corresponding weight matrix. Okay. and we'll divide the matrix into heads, smaller heads, and then each head has an output. Okay, so we call this head outputs. We declare that as a vector. Okay, each head outputs will be put in the vector, will be saved in this vector. So to calculate the attention of each head, we use a straightforward method. It is not efficient, okay, but it's simple and easy to understand. Okay, we just declared the size of each head. Okay, for QKV, we call that QH, KH, VH. Okay, so it has the dimension dk. dk is d module divided by a number of heads. Okay. And then we copy the values, corresponding values, okay, into the head. Okay. Using this method to copy that into QH, KH, VH, and then we call this function scaled attention. We just mentioned the QH, KH, VH to do the matrix multiplication. It's very straightforward. It's not efficient, but very straightforward. Because it is not efficient because we need to do the copying. Okay, actually we don't need to. Okay, but this is very clear. And then the mask, which can be true or false. Okay, it is an input parameter. Then we concatenate the heads. Okay? We put all the heads into this vector head outputs. Okay? And now we put all of them, concatenate all of them into this matrix concat. Okay? And then finally, we do a linear projection. Okay, basically multiply the concat with the output matrix WO. Okay, to give the final output and return the final output. So there's the multi-head attention. Okay, so this is the feed-forward class, and well, we have an update ways function here, but we don't have any ways update discussion here. Okay, but we'll discuss that in the future. Now this is the encoder. We discussed this before. So this function compute output will compute the output of the encoder. Okay, E here. So first, it does it calls the compute attention. Okay, to do the multi-head attention computation. Okay, it's not masking, so that's why it's false. And then we have an norm. Okay, and this will go into feed forward, and then another norm. Okay. So this will give us the output, and it is E here. Okay. And for the decoder, okay, so it is this part, this module here. So the decoder has inputs from here, the X, and also the cross inputs from the encoder E. Okay. So to do the computation, we first do a masked multi-head computation. So we call compute attention with inputs XXX for the QE key and value. Okay. And the true means we are doing the masking. Okay. And then after this, we do an norm here, and then this will go into the multi-head attention, the coarse multi-head attention. Okay. Here, the QA input is X1 from here. Okay, this is actually the query, and then this the key and value. Okay, from here, key and value from here. Okay, and it is not masking, so it is false. Then we do the add norm. Okay, add norm here, and after that is feed forward another add norm. Okay, so feed forward. Okay, add norm, and then return the final output. Okay, so there's the decoder implementation, quite straightforward. Okay. And this program, this routine is for testing the decoder. So we use 2 heads. Number of heads is 2. Okay, so this is the source sentence, the waves, the crash force rate against the source. Okay, and again we use this file to do tokenization, as discussed in a previous video. Okay, we create the embeddings and add that with positional encodings. So this will be the inputs to the encoder. And then we do the same thing for the target. Okay. So target tokenizer. Okay, and we use another file, corresponding file t1.x. The target sentence would be like this, is in Spanish. Okay, and also it does the same thing. To the embedding and positional encoding, so to generate X. Okay, so we to print out the target embeddings with positional encoding. Okay. We also print out the input embeddings, and also print out the outputs from the encoder, okay, which will be inputs to the decoder. And then finally, we print out the output decoder, and so we will see how they look like. Okay. Now this is a symbolic file to compile all the files. Now let's copy all this and compile that and see how it works. You can easily copy this by highlight them. Just do all this and copy it. Okay. We have just copied all the files to this directory. Now let's take a look at those files. util.h okay. And util.cpp, so the same as those you just saw, and transformer.h, the header file, and .cpp, the transformer classes, and the test, and the make file. Okay, now we can make. So create the executable test decoder. Okay, so these are the tokens of this original sentence. So there's the source sentence tokenization, and these are the embeddings of input to encoder, and this is the output of the encoder. So it is 8 times 8. This is the target sentence, target tokenization results, and this is the target tokens. You can see that it has 9 tokens, so it is 9 times 8. Okay. Input to a decoder, and this is the decoder output. By the way, t1.txt and t.txt are the files used for tokenization. This is the source file, t.txt, okay. And this the corresponding target files. Now, in case you want to explore some features, you can easily modify some functions and see how it works. For example, if you want to examine how a masked attention is different from the unmasked attention, you can insert code here to print out the matrix A, okay, the attention matrix. Suppose we could insert code like this. If mask, then we print our masking A and print the matrix A, the attention matrix, okay, that we obtain here. Oh, maybe we should put it up here. Okay, sorry. Okay, insert here. Okay. So if it is not mask, okay, then we print out the message no mask A and the matrix A, okay, and then get care will give a pause. So we could create the files, make clean, and then make again. Okay, so now we can execute the file. Now this is the output of encoder. Well, not output yet, actually is the attention A. You can see that every entry has a value. Okay. The other attention, okay, and others are as before. And now this, so that was for the encoder. Now for the decoder, we have the masking A. Okay, you can see that these values are 0. Okay, the upper triangular values are 0. Okay, and other masking A. Okay, and no mask again. So the cross image A. No mask. Okay, so you can modify the program and play with it. This wraps up our discussion on this topic, okay, decoder of an AI transformer in C++. Thank you for watching, and I'll see you in the next video.